Good morning and good afternoon, and welcome to the April Pacific Northwest Drought Early Warning System Drought and Climate Outlook webinar. My name is Britt Parker, and I'm with the National Integrated Drought Information System. This bi-monthly webinar series is hosted by NIDIS, the USDA Northwest Climate Hub, and the Oregon Climate Change Research Institute. It is designed to provide partners and other interested parties in the Pacific Northwest with timely drought and climate information. Each webinar will be tailored to reflect recent, current, and forecasted conditions and climatic events, but will also include discussions of observed impacts and other relevant updates from across the region. Webinars and recordings and other supporting materials will be posted on drought.gov later this week. And just to note that after today's webinar, you'll have the opportunity to provide feedback that will help us improve this webinar series. So please take a moment to tell us what you think. Today's speakers include the Climate and Recap Current Conditions with Nick Bond from the Office of the Washington State Climatologist. We have Jeffrey Walters with the National Weather Service Northwest River Forecast Center with the Seasonal Conditions and Water Supply Outlook. We'll then hear from Allison Cobb with the Centers for Western Weather and Water Extremes at the University of California, San Diego, talking about observing and understanding atmospheric rivers. And finally, Samantha Stevenson from the University of California, Santa Barbara will present on a manuscript released last year called 21st Century Hydroclimate, a continually changing baseline with more frequent extremes. We will be using the Q&A box at the right of your screen for questions during the presentations, and we'll address those and additional questions during the Q&A period after the 4 presentations are over. Before we begin the presentations, we wanted to highlight the partners who make this webinar series possible. The Northwest Climate Hub develops and delivers science-based, region-specific technologies and practical information that will assist agricultural and natural resource managers with climate-informed decision-making in Idaho, Washington, Oregon, and Alaska. I'll put their website in the chat box after I complete the presentation, but definitely check out their website for more information. The Oregon Climate Change Research Institute is a network of dozens of researchers at Oregon's public universities that work closely with other public and private entities. OCRI is housed at Oregon State University and advances understanding of regional climate impacts and adaptation and cultivates climate-informed communities. And I'll drop their website into the chat box as well. NIDIS was established in 2006 by public law with a mission to improve the nation's capacity to proactively manage drought-related risks by providing those affected with the best available information and resources to assess the potential for drought and to better prepare for, mitigate, and respond to the effects of drought. NIDIS is building the foundation of a national drought early warning system through the development of regional DEWS, where networks of partners and stakeholders share information and actions that help communities cope with drought. Each DEWS has many of the same base ingredients, but ultimately their own flavor to reflect the needs of their region. The Northwest DEWS was officially launched in February of 2016, and our strategic plan and information on current activities is available on drought.gov. Finally, to facilitate our early warning system, more precipitation observations are needed. We encourage you to join COCOROS, the Community Collaborative Rain, Hail, and Snow Network. This is a unique, nonprofit, community-based network of volunteers of all ages and backgrounds working together to measure and map precipitation, rain, hail, and snow, as well as condition reporting. Observation by COCOROS observers of precipitation events or the lack thereof are important to capture and improve our understanding of weather. To become a volunteer or to learn more, visit cocoros.org or contact your state coordinator. And in a moment, I'll put their names and emails into the chat box. But first, I want to turn it over to Nick Bond.
All right, thank you. And let's see if I can share my screen here.
Okay, it should be coming your way.
So you should be seeing a rather snowy landscape in southeast Idaho.
We are not yet seeing your full presentation screen. There we go.
Okay.
Perfect.
Now is it okay?
Yes, it is.
Okay, very good. Yeah, so what I want to, kind of emphasize here is while the national media has properly focused on all the weather that has come into the California and southwestern U.S. this past winter, the winter is hanging tough in the Pacific Northwest. Maybe I'm getting a little bit ahead of myself, but looking at the water year so far as a whole, starting on the 1st of October through the middle of last week, on the left shows the temperatures relative to normal, and on the right, the precipitation in terms of a percent of normal. And for the winter as a whole in the Pacific Northwest, it was definitely cooler than normal, especially in the interior Pacific Northwest, and to a bit kind of surprising, in parts of the Pacific Northwest actually drier than normal. And I'll say a little bit more about why that was a surprise, but the interior, much of the Pacific Northwest, the interior parts were on the wet side. Overall, it was the 33rd coldest back to the late 1800s and the 32nd driest, but that the driest one really reflects how much leverage west of the Cascades has, because it's just naturally a wetter place. Looking at the last couple of months, complete months, February and March, here, time series for the Pacific Northwest. On the top, temperature, on the bottom, precipitation. You can see just at the far, end of the right of the time series there, just how cold it was the last couple of months in the Pacific Northwest. Following a very cold February and March in 2019, if you look at this kind of late winter period, last 5 years, you have to go back a long ways to have another 5-year period quite as chilly. It's also been a little bit on the dry side this past couple of full months, and in recent years. There was other events, not just earlier this month in the interior Northwest. This is the scene from Crater Lake right after a snowstorm in late February. That's a snowy place, and so maybe not so unusual. What was kind of unusual is there was a fair amount of snow right down to the coastal region, and so this little guy was the beneficiary of that. I see that. Call it an enrichment session with frozen crab claws and toys. I can't remember the last time I was given an enrichment session, so maybe, yeah, these guys have it good. All right, let's talk about the last 30 days. And just following up on the point that winter is hanging tough for the entire Pacific Northwest, and this is from late March through last week again, it's been considerably cooler than normal. And they're kind of a more spotty in terms of precipitation on the right, with now the coastal regions of the Pacific Northwest doing pretty well recently. And just from a kind of time series perspective, going back to southeast Idaho, you can see that at least in that spot, a pretty typical sort of precipitation accumulation since the first of the calendar year, with that big snowstorm in early April showing that more recent rise. I think some of the public perceptions are kind of interesting. Here in the Seattle area, we've had a fair number of rainy days, but not very many big rain days, and so our precipitation is definitely down for the water year as a whole. But if you were to ask most people, like, oh, it's been raining all the time. And in fact, the Seattle Times got into the act there saying, oh, the most rainy weekends in the past 5 years, which doesn't really disturb me, but again, it's public perceptions aren't always quite right. All right, so what are some of the data showing? Here I have the 14 days ending late last week, what the stream flow is across the Pacific Northwest relative to normal. I'm not sure exactly how meaningful this necessarily is, given that we're still melting our snowpacks and so forth. All those blue dots in the Willamette are showing some of the decent rains they got down there over the last month or so, and also in Western Washington. And there's some of those redder dots showing much below normal stream flows, merely reflect the cold temperatures, and that especially at higher elevations, some of the melt hasn't really occurred in earnest. And what I think is more significant this time of year is what kind of water we have in storage. And here, just from the Bureau of Reclamation, the collection of reservoirs there, I show three different groups. On the upper left, the Yakima in central Washington, the lower left, basically the eastern Oregon set of reservoirs, and then in the lower right, those in the upper Snake River Basin. And for the most part, these the reservoirs are in decent, if not great shape. In the Yakima system that I'm more familiar with, they're considering that there may be some very minor restrictions on some of the junior water rights holders this summer, but probably be okay. You can see in these teacup diagrams that there are some reservoirs that aren't very full. But when we go to the snowpack here, last week, you can see in southern Idaho and much of Oregon, the snowpack is actually in pretty good shape. And it is, and so I think there's going to be some filling of those. Well, there's sure to be some of the filling of those reservoirs. One thing that's kind of interesting is up in the Canadian Rockies, it's not in that great a shape. It's not terrible, but some of these basins, 80% or so. And so that will certainly have implications for the total amount of flow in the Columbia River system. All right. One thing that is playing out right now, and it's going to be interesting to see just how it is resolved, is the effects of the dry late summer and early fall we had last year. This shows a kind of a vertical curtain time series from early last year through close to the present time of the soil moisture in terms of percent saturation at Harts Pass in the North Cascades. It's in fact not at 65,000 feet, but actually 6,500 feet elevation. And what's kind of interesting there is that the really dry late summer and fall meant that before the soils really froze up in the winter, they didn't get the burst of rainfall and the moistening that they usually get that time of year. And so right now we're coming out of the winter season with a really dry subsoil moisture contents. And so depending on just where you are, those deficits are going to have to be brought up with some of the snow that's melting before there can really be substantial runoff. And so how much of an effect that's going to make is going to vary from place to place. It is recognized in terms of the total moisture from a percentile basis that, as reflected in the UCLA drought monitoring system, in that The plot at the lower right shows the combination of the subpar subsurface soil moisture, plus in many places a pretty healthy snowpack, and the consequence is kind of a mixed bag in terms of total soil moisture contents. Now, the river forecast setters do take into account soil moisture contents in their river forecasts, of course. I personally am unsure how accurately that can be done due to the limitations and just the base data that it goes into those model runs. Certainly different soil moisture representations have different kind of handles on what's happening, but ultimately we're just going to have to wait and see how our dry fall is going to play out in terms of the eventual stream flows this spring and early summer. This has been the third La Nina winter in a row. This is a series of SST anomaly maps for a week in February going back the last 3 years. The La Nina, as you'll hear from Jeffrey, is definitely it's over and was waning by the late this winter. But also one thing I can't help but notice is the rather persistent warm water that's been there in the central North Pacific for a number of years now. During here, looking at the January to March period, during most La Ninas, we have a weaker elution load than normal. If you look at the geopotential height related to the pressure aloft, it's higher than normal pressure south of Alaska. Weaker, lower pressure geopotential heights over Western Canada, with the consequence of more northwesterly flow into the Pacific Northwest than usual during the late part of La Nina winters. And that usually means the west slopes of the Cascades and the Rockies do pretty well. And as you can recall, that hasn't been the case this time. And that hasn't been the case because while we had a high pressure off to the west there, south of Alaska, instead had a very unusual upper level trough, low heights over Northern California into the Great Basin. And so what did relatively well this winter are the kind of more the east and south facing slopes in the Pacific Northwest, which is again a surprise with La Nina. All this is reflected in the representation of the drought conditions from the U.S. Drought Monitor. The problem areas are in the northern Idaho, northwest Montana, and especially eastern Oregon. That the extreme drought there is just the really longer term precipitation deficits that have accumulated there in eastern Oregon. All right, just to sum up, again, Pacific Northwest, a cool and dry winter, and something we didn't necessarily really expect in terms of the dry side with La Nina, but that's the way that's the hand we were dealt. Our snowpacks are in decent shape in the north, and I would say more in good shape in the south. But there are still some problematic areas from a drought perspective in parts of the Northwest. And again, what we're seeing is kind of the result of a really unusual circulation that featured a lot of cold storms into California, and of course benefiting their water supply problems. And finally, I think we're all looking forward to what Jeffrey's going to tell us about what's liable to happen in the Pacific Northwest in the next month, season, year, whatever. And in particular, we've appreciated now how much of a difference late spring can make. And is it going to be the warm, dry one like we had in 2021 that sets the stage for an early and intense heat wave, or is it going to be the wet and cool one that we had last year? So with that, I will close, and thanks for your attention.
Thank you, Nick, and we'll turn it over to you, Jeffrey. Perfect. And we are not hearing you yet.
Yeah, I was on a roll there. Okay, let me try again. Thank you, Nick, for setting me up and you're sharing your presentation. A lot of the information I'm going to share is going to build off of what Nick talked about, and so hopefully I can give some context of how the information of the current hydrologic conditions are playing a role in water supply volume forecasts and the expected outlook for seasonal volumes. Again, my name is Jeffrey Walters. I'm a senior hydrologist with the Northwest River Forecast Center. We're part of the National Weather Service and NOAA. We provide 10-day forecasts, river forecasts throughout the Pacific Northwest and seasonal volume forecasts. I'm going to be talking about the later today. And one thing I want to add is if you have any questions about my presentation or anything else in general about water supply volume forecasts, that email below is a great place to reach us at, and I'll get to one of our hydrologists who can help answer any questions you might have. Okay, so the Columbia River Basin is dynamic. There's a lot going on in water supply on a micro scale, but we're going to talk macro. We're going to paint some broad brushstrokes here and just talk in generalities. And as Nick pointed to, precipitation generally in the Columbia River Basin has been below normal, but it's been cold. And so despite the below normal precipitation, and because of the cold temperatures, snowpack for much of the region is above normal. And snowpack's a big driver of water supply volume forecasts. And the other point is, as Nick kind of pointed to with some of the plots, is soil conditions regionally for the Columbia River Basin are below normal. So those two factors, the snowpack and soil, are competing against each other. The soil, if it's drier than normal, it's going to take a little bit more of that snowpack from that melt before the allowance of a river runoff. And that's reflected in our water supply volume forecasts. You might look at the snowpack and think that the expectation being that water supply volume forecast for the snowmelt season is going to be above normal, but that's not actually the case in our current line of thinking. It's due to the soil conditions; those are actually driving down and having a negative impact on those water supply volume forecasts. And then to answer the big question of like how spring's going to play out, we're really going to see the impact of future weather patterns for the remaining months. Those volumes are going to really. I'm going to show you how those volumes really, the uncertainty in those volumes are going to play out in June and July. Those are the months that are going to benefit if we have a wet spring or a wet spring, or suffer if we have a drier spring. So I'm not going to spend much time on this. You guys are all probably familiar with the Columbia River Basin. The one thing I want to talk about is we're going to focus on the April to September period. And why is that? It's because we're dealing with a snowmelt driven basin. The plot on the bottom there is the Columbia River DEWS, which is kind of our index for total runoff in the Columbia River Basin. And this is adjusted, so normalized to remove any upstream regulation. And this is, black line is just the normal runoff we would see annually. You see May through July are the big runoff months, and that's because of when spring and summer starts to warm up, melts the snowpack, and that's when we see the higher runoff. And the other thing I want to point out is the map on the far right. That is some key contributing basins to overall runoff in the Columbia River system. And I've got a pie chart there of annual runoff volume, how much they contribute to that total runoff at the DEWS. And you can see the upper Columbia, Kootenai, and the Pend Oreille, and the Snake are the four biggest drivers, accounting for well over 50% of the total runoff. And the upper Columbia is definitely the most efficient per area at 20%, but Snake is actually the largest provider of runoff. But I would say upper Columbia and Kootenai and Pend Oreille above Grand Coulee are a big component, comprising over 50%. And just really briefly go over our forecasting technique we do here. our forecast, we issue forecasts for a number of seasons and months, water supply volume forecasts every day. They count for the current basin conditions of the two main components of water supply volume forecast, snowpack and soil moisture. We'll go over that in more detail in subsequent slides. And then we also take into account the next 10 days of weather patterns, and those make up what our water supply volume forecasts. And then we add uncertainty in those water supply volume forecasts in ensembles, but by considering historic pairs of observed data for the last 42 years. Again, we're going to focus on April through September volumes. And if you were to look at one of our water supply volume products issued daily for a forecast point, they are summarized, those ensemble members, as box and whisker plots. So this is seasonal precipitation, one of the factors that plays a role in what our snowpack looks like. The map on the left there is the seasonal precipitation up until Friday. Those are subbasins colored according to their seasonal precipitation as a percent of normal. It should look very similar to the plot that Nick shared earlier. And just generally, you know, like Nick showed, that a lot of yellows and oranges, meaning drier than normal conditions, with the exception of the Snake. And then if we were to look at the whole basin at the DEWS, the total precipitation for the entire Columbia River Basin, we have accumulated precip on the plot on the right, traveling through time. The blue is this current water year, and the dash is the 30-year normal. And we've pretty much been tracking exclusively for the entire Columbia River Basin below normal. Right now, we're at 79% of normal. And then on the flip side of things, is our seasonal temperature. So it's been drier than normal, but it's been colder than normal. This again should look very similar to the information Nick shared. On the left is a map of seasonal temperature relative to normal, and blues and light blues below normal. So it's been cold. It's been a cold winter. In fact, if we look at the map on the right, we have temperature departures for just this month, so last 3 to 4 weeks. You can see April is typically thought of as kind of the beginning of snowmelt season, but unfortunately, this isn't a typical year. That snowmelts, you know, those cold temperatures are delaying the onset of snowmelt. So we're starting to see the byproduct of that, of a later runoff than maybe we would typically normally see. So despite the below normal precipitation in the Pacific Northwest, and due to the colder temperatures, snowpack is actually pretty healthy. This is almost just a different date, but the same plot that Nick shared of the NRCS's generalized basin SWE states as a percent of normal. This is the map on the left. You see almost everywhere, with the exception of the Kootenai and the Pend Oreille, that all of these basins have snowpack that are above normal. So that's good for water supply. And however, and on top of that, as temperatures over the last month have indicated, this map on the right is that the snowpack isn't quite ready to run off. And one tool that we use to track kind of the onset of snowmelt, when the snowmelt's ripe enough to run off, is snow density. And we don't have to get into too much detail besides that the higher the density, the riper the snowpack is and ready to run off. And these colors are at SNOWTEL and other partners' snow monitoring stations. And this is the snow density as of last Friday. And blues and greens would be that the snow isn't ready to run off. Whereas as you get yellows, oranges, red, it's getting to be a riper snowpack and ready to run off. And we are 3 weeks into April, the beginning of the snowmelt season. And we have a lot of stations that are still where the snowpack is still locked up and not ready to run off, indicating that we're going to see a late freshet season. So one major component of our water supply volume forecast, because we're a snowmelt dominated Columbia River Basin, is the snowpack. And then the other component is soil conditions. I really liked the map or the plot of the SNOWTEL gauge of the soil moisture conditions at a site, SNOWTEL site that Nick shared. I think that's kind of great and really kind of is a snapshot of how our soil conditions played out going out of kind of a dry, hot summer into this water year, that those dry soil conditions kind of got locked in. And Nick's right. It's definitely difficult to look at those singular gauges and make decisions on how the state of the whole of these larger basins of their soil conditions. What we typically use, in the wintertime, in the Columbia River Basin, most rivers are in their base flow conditions, meaning that most of the precipitation in the wintertime is falling as snow, not running off into the river, and the rivers are at their lowest base flow conditions. And we really use that as a snapshot or an index for the soil states. Usually the lower the base flow, the drier the soil states. And we've had historically low base flow river conditions this winter. So this is a snapshot of the adjusted runoff for this water year as of February 28th for locations throughout the Columbia River Basin. So this is right before when we'd start to see snowmelt season. So kind of our last look at the base flow conditions and the soil states. And you can kind of see coming into the spring freshet, almost universally, the rivers were below normal conditions, which was really kind of a good indicator for us. The soils are below normal, and our states that we use for our water supply volume forecasts kind of reflect this. And then the map on the right is just another tool that kind of hopefully illustrates to you that, we had dry soil conditions. This is, again, the drought index, similar to a plot that Nick shared, but just at the end of last water year, that pretty much universally for the Pacific Northwest, we were at least abnormally dry to exceptionally dry throughout the Columbia River Basin. So I would say this time of year, soil states and the snowpack are kind of the major drivers to our water supply volume forecast, but a more minor component this time of year would be our 10-day precip volumes. So on the left is a map of our forecasted QPF over the next 10 days, how much precip we expect over the next course of the 10 days. That's a map on the left, and the right is what those totals are in context of climatology. And you can kind of see that not helping the matter is that it's going to be drier than normal over the course of the next 10 days. And that's going to slightly drive down water supply volume forecast, but not as much as maybe if we saw this kind of map maybe in June and July when snowpack is so important.
Hey, Jeffrey, this is Britt. I'm sorry. If you don't mind wrapping up in the next 2 to 3 minutes, that'd be awesome. Sorry.
Yeah, no problem. That's great. So we'll just wrap it up with, this is the water supply volume forecast. This is, we're gonna give those major basins that I shared earlier, but we'll also provide some sub-basins where larger dams reside. You can kind of see the water supply volume forecast reflect, even though that we have above normal snowpack, we have drier than normal water supply volume forecasts. And that's because of those dry soil states. And you can kind of see this map on the left. We see a lot of yellows, but we also do see some blues in the snake. And if we look at the table on the right, at the DEWS, we have 85% of normal. And that's because of how dry things are up above Grand Coulee. And so the soil conditions are really playing a role in our water supply volume forecast. And I'll just leave it on this. This is kind of a great, ties it all together. This is a map of monthly volumes observed and expected. The blue bars are the observed runoff for each month, and the green dots are normal. You can see the base flow overall for the entire basin has been below normal from October through April. And you can kind of see the variability in the water supply volumes that we expect over the next month. And I think what's misleading is that there seems to be a lot of variability in how the runoff is going to play out, but really that's not May really isn't a player in an indicator of what the large runoff, the volume of snowmelt runoff is going to be. It's really more a volume of timing. It's really June and July, which are really going to tell the tale of whether we have above normal or below normal water supply volumes. And then I'm just going to skip the last slide and just wrap it up that it's really snowpack is above normal, soil conditions are dry. Those two components are competing each other, and that soil conditions are really playing a role due to the dry soil conditions going into this water year on our below normal water supply volume forecast for the big picture on the Columbia River Basin. Thanks.
Great, thank you so much, Jeffrey. I'll turn it over to Allison now to talk about observing and understanding atmospheric rivers, and just remind everyone, if you have questions for our speakers, go ahead and type them in the question.
Great, hi there everybody, just bear with me one moment while I share my screen. Britt, can you see everything okay?
Yes, looks good, thank you.
Perfect. Okay, good morning, good afternoon, everybody. So I'm just going to give you a very brief outline to observing and understanding atmospheric rivers. And this is work that I did at the Center for Western Weather and Water Extremes at Scripps Institution of Oceanography at UC San Diego, with many collaborators who I won't have a chance to mention all of them. So this is what I'm going to be talking about, really focusing on what are atmospheric rivers, why are they important, a summary of some observations and their uses, and then I'll go into some detail on atmospheric river reconnaissance, followed by a one-slide summary. So here, hopefully you can see this animation, and here we can see the US, and in the animated colors, that's total precipitable water. So that's the water, carried in the atmosphere. And this is taken from the 9th to the 31st of December 2022. And that was a very wet period. And you can see that these kind of blue, yellow, green bands keep hitting the west coast, bringing a lot of moisture to those coastal areas. And atmospheric rivers, or ARs, which I'll probably refer to in the future, are measured by integrated vapor transport. So that's really the combination of the amount of moisture in the atmosphere with the winds transporting that vapor. The total instantaneous water flux in an average AR is equivalent to the flux of liquid water into the Gulf of Mexico from 27 Mississippi rivers. And they're also responsible for heavy rains, bringing 92% of the West Coast's heaviest rains. ARs, atmospheric rivers, also have a lot of impacts. As well as bringing beneficial rain, they can also cause damage. So flood damages increase exponentially with AR category. And AR category is based on the duration and the intensity of that precipitation. Okay, so here's some observations. On the left is a drop sonde where that tube is about 2 soda cans big with a parachute attached. And these are dropped out of aircraft at maybe 10 kilometers or so. And they're dropped out of aircraft and they take recordings of temperature, pressure, moisture, and wind through that little parcel of the atmosphere. Radio sondes go the other way. So we blow up these big balloons on land and release them into the atmosphere, and they also have those same sensors on them. And then on the right here, we can see a drifting buoy, and these are deployed in the ocean, have a lifetime of a couple of years, and are out there recording observations in the ocean, which are areas that are very under-observed. So these ones are in situ observations, which are very useful, but there are huge range of other observing tools. For example, airborne radio occultation, or ARO, radar, and satellite. So why do we need observations? One use is for data assimilation. So this is where you're adding observations into a weather forecast model, and it gives you improved forecasts. There's lots of different statistics that show you these examples, but I just thought I would highlight one here. So assimilation of in situ observations from the campaign I'm going to talk about in a moment increases the use of tropospheric satellite radiance data by 5 to 10%. So that's saying by using these in situ observations, the model is then being able to use much more satellite data at the same time. So that's a really interesting finding. And secondly, science questions. We use observations and a whole range of other tools to improve our understanding of atmospheric rivers. And there's many papers talking about how we get to understand ARs from observations. For example, I had a paper where we identified different sectors and we could characterize the qualities of different areas of the atmospheric river. There's been work that shows new cyclones that develop near a pre-existing AR strengthen 50% faster than those without an AR nearby. And there's been many papers that go towards understanding the physics that control AR intensity. So atmospheric river reconnaissance, or AR recon, is run out of CW3E as part of UCSD. And this list is showing you the PI, co-PI, and a lot of sponsors and partners who are involved in this huge collaborative campaign. And on the right here, you can see just a logo cloud. So all of the different logos represent people who are working on this campaign back in 2021. And I'm going to talk a bit further about that work as that's in a published paper. So these logos represent the different institutions. There's research institutions, universities, etc., and government labs. And there's all various teams that we have, for example, forecasting teams, flight directors, flight planning teams that you can see on the right-hand side. And the goal of AR Recon is to support water management decisions and flood forecasting by developing and testing the potential of targeted airborne and buoy observations over the Northeast Pacific to improve forecasts of the landfall and impacts of ARs on the US West Coast at lead times of 1 to 5 days. So on the left-hand side here, you can see a map with the US West Coast out into the Northeast Pacific. And this is one IOP, or one intensive observing period. So the colored contours are showing you IVT, so that's really showing you where the AR is. Then we've got the contour lines in black colors, in black lines, sorry. The black straight lines are showing you the track of the flight that's flying out of Hawaii, and all of the black dots are showing you where dropsondes were launched out of that aircraft. So you can see that they're launched in the AR, trying to sample that air mass. On the right-hand side, here you can see the observations that have been collected as part of this campaign over the last several years. And really, year on year, they're increasing the amount of observations that are taken. And this year was very wet, at least early on in the season, and there ended up 39 IOPs and 51 flights going out. On the left-hand side, here you can see the precipitation from 2021. So this is the winter period. And there's a lot of red and yellow where we had intense precipitation where the atmospheric rivers made landfall. And you can see the atmospheric rivers are shown with those orange and blue lines. And to decide where to sample these atmospheric rivers, we have 3 different tiers. I won't go into detail about these, but there's a paper you can refer to if you want more detail. But really, it's based on sampling the essential atmospheric structures of those systems and areas of forecast sensitivity, where if we get more in situ observations, we're likely to improve the forecast rainfall at landfall. This is showing you again in 2021. The left-hand side is the period the AR Recon was operating, and we've got the number of dropsondes. And hopefully you can see where there's each step going up, there's a number, and that's the IOP number, or each time we went and deployed observations. And they're all collected into different sequences where we had contiguous days of making observations. And on the right-hand side, it might look like a bit of a messy map, but this is just showing you the dots where all of those dropsonde observations were taken. So really spanning a huge amount of the Northeast Pacific. This is showing you the 4 radiosonde sites that we had during AR Recon 2021. So we had Bodega Bay, Yuba, Salton Sea, and Scripps Institution of Oceanography. So this is where those balloons were launched from land and went up into the atmosphere. And they were generally launched during the time an AR was passing through. So really, that's just a very brief summary, but I wanted to highlight the importance of ARs. They bring most of the US West Coast precipitation and bring beneficial rain, as well as some damaging precipitation and flooding as well. There's a huge range of observations out there, including in situ, such as dropsondes and radiosondes, as well as all sorts of satellite data as well. And observations are used to improve forecasts through data assimilation, and also to improve the understanding of ARs through asking scientific questions. Atmospheric river reconnaissance, or AR Recon, is run in the winter season in the Northeast Pacific and principally deploys dropsondes, radiosondes, and drifting buoys. And as I mentioned, there's this paper that gives a nice summary of AR Recon 2021. It tells you kind of how we make many more of the operational decisions with regards to flying, and gives you some nice summary statistics of that season. So that was a huge collaborative effort with around 25 co-authors. So that's everything from me. Thank you.
Thank you so much, Allison. And as I hand over the presentation to Samantha, we do have one question about the 2017 AR Recon data. and where someone might be able to locate that. If you have something to share, you can chat it to me and I'll share it with everyone.
Hi, I would just mention now quickly, I'm not sure if you saw on that table, yes, so it goes 2016 and jumps to 2018. Unfortunately, that was before my time at the centre and when AR Recon did not operate in 2017, but from 2018, it's been every year.
Okay, thank you so much.
Thank you.
And Samantha, we'll turn it over to you.
Okay, sounds great. Can you hear me and see my screen all right?
Yes, thank you.
All right, perfect. Wanted to make sure I was sharing the right one. Yeah, so thanks for having me. This is my first time presenting at this webinar series. This is exciting to be here. Yeah, I wanted to share some results from, as Britt mentioned, a study that came out last year, which is not, directly observationally based in the Pacific Northwest, but I think is extremely relevant to be considering as we're seeing the evolving impacts of climate change expressed in the Pacific Northwest and other portions of the Western U.S. So this is just my collaborator list here. But, I'd like to start just by emphasizing the two major points. And so you can read them here on the slides, but essentially, because we're now seeing, as I mentioned, the evolution of climate change being expressed continuously, these climate-driven trends in the soil moisture are in fact so large that if we can, like what we used to think of as being exceptional drought events are simply becoming normal conditions. So in other words, the background trend is largely exceeding what we used to consider as thresholds for soil moisture, which would have been considered extreme drought. So we need to take that into account when we're defining a drought event is kind of one major point that I wanted to make. And then the other point I wanted to make is that even when if you are able to remove the effect of background climate change from the long-term trend in rainfall, extreme events, such as like the ones that Allison was just talking about, are projected to increase in intensity in the future, even relative to an ever-changing new normal. So and I think we've seen a lot of this play out in the past 2 years in the Western US. So we're seeing these background trends, sustained depletions in many reservoirs around the West, but superimposed on extreme rainfall events that, like the ones that we just saw in California, which we had just an extremely wet winter down here. So you can check out some of these results. This is a paper that came out in PNAS last year with the same title as my current presentation. But I guess wanted to make one point quickly, which is that all of these results are based on climate model projections, but the results are fairly robust in my opinion. So, well, what am I talking about here? So there's this idea that droughts exist, right, and can be defined as specific events. Typically, they're defined, well, in many cases, they're defined based on threshold exceedances. So in this case, I'm showing an idealized example where there's a soil moisture time series for one model projection from the southwestern US, right? So what we have historically considered to be a drought is oftentimes a soil moisture being below some number, right, relative to a reference period, right? So this is what you would, if you look at the black line, over the 1950 to 2000 period, you would use by that definition, determine that, say, the 1980 to 2000 period would correspond to a drought, which is fine as long as you're in a stationary statistics realm. But the problem is that that's not the situation that we find ourselves in at the moment because of climate change. So if you follow the black line out to the right hand of the plot, then you quickly find that by that static definition, the entire 21st century would be considered to be one continuous drought event. And so that definition becomes no longer as useful from a planning perspective. If you are then able to remove that trend, however, you see the red dashed line where the mean is now by construction roughly 0, and then you could consider variability about that trend. And so this is a particular definition that can be used in the tree ring literature and in kind of like the decadal variability literature. So it's the idea of like the California, for example, having been in a mega drought or a drought since the late 2000s, right? So we were trying to determine, how much of this behavior is actually due to the trend, and can you get more insights when you remove that background trend using climate models? So I don't have time to explain much about this idea of climate ensembles, but just briefly, the future models that are used for global future projections are now being run not just once, but several dozen or even up to hundreds of times, and is just by varying the initial conditions slightly. And this is a way to generate larger statistical robustness and to be able to assess extreme events in more detail. So these results are going to use 4 different climate models shown here under the same future scenario, so a high emissions RCP 8.5 future projection. And these models are run 30 to 50 times each. So what you can learn from this is that when you use all of these ensembles and calculate the risk of this multi-decadal megadrought, so this idea of a megadrought being where the 15-year average soil moisture is below a 0.5 standard deviations. So it's a measure of the kind of long-term slow variation in drought. What you get when you combine the estimates from all 4 of these climate model ensembles is that the future change in the risk of megadrought, so the proportion of the time in which you would be considered to be in megadrought conditions, increases over a large percentage of the land surface. Not everywhere. Importantly, there are regions which are projected to become wetter, in fact. So those are like the stippled places are places where there is disagreement amongst projections of future climate change, but there are large regions of intermodal agreement. So those are highlighted in the boxes here. And in, I guess in the Pacific Northwest, there's not as much agreement amongst the ensembles. In the central to western US and Mexico, there is substantial aridification in parts of Western Europe as well. So there's like many places where this just changes in soil moisture are extremely large. But in fact, the nice thing about the model ensembles is that you can average them all together and use that to get an estimate of just the forced trend, right? So the effect of climate change itself in the absence of kind of year-to-year random variability. Then you are able to remove this and recalculate the risk of these megadrought events. And when you do that, you see that the statistical significance of these risk changes are much lower. So we saw a large proportion of the land surface becoming drier in the previous figure. Here, that's no longer the case. So the change in megadrought risk, or I guess this is megapluvial risk in this case. So the increase to wet versus dry events is kind of just like this, the other half of the coin here. When the point is that there are very few regions around the world which continue to show a change in the statistics of either wet or dry events, according to this multi-decadal definition, when you have removed the effect of the background trend. So I kind of view this as if we can determine how to adapt to a continuously evolving background trend, then the exceedances relative to what we would consider normal as a function of time are not that different. But the important thing is, like, from an adaptation perspective, or from an infrastructure perspective, is that we do in fact need to account for continuous changes to what is normal. So this figure is showing just a time of emergence calculation. So basically, what does that mean? So it's saying that when you're going to retain your megadrought definition, and then when you average all of your model simulations together, you can see what that long-term trend in the forced response of soil moisture might be. So when the average change, or the average value of soil moisture, goes below the threshold that you had defined for what is a mega drought, then you consider the mega drought conditions to have emerged. So it's kind of like that time series figure. So you will never return to a non-drought condition in the places where the time of emergence here exists. All right, so basically here, the browner the shading, the earlier megadrought conditions have emerged as just being normal. And in fact, in many locations around the West, including actually parts of the Pacific Northwest, in this case, the normal state, so the emergence time, is in fact before 2020. So megadrought is becoming the new normal, in which case we need to take this into account in assessing just the overall amount of moisture that we can expect to be existing in the background. So this is distinct from the results that we've seen for individual like water years, or it doesn't mean that extreme events are no longer going to happen, but on average, we're seeing the emergence of these background drought conditions. So this brings me to my next point, which is that extreme rainfall is projected to become stronger in the future, even compared to a new normal. So just very briefly, I have different definitions for wet and dry events here, so which are roughly analogous to the 2010-11 wet extreme in Australia, or the 1976 to 77 winter in California. This is like a seasonal accumulation of precipitation exceeding the 99th percentile over the late 20th century. And then a dry event here is analogous to the 2012-2016 California drought, where the 3-year average precipitation is below the first percentile calculated, or the percentile calculated according to the late 20th century distribution. So it's kind of an interannual definition of a wet or a dry period. And so when you consider this, that extreme precipitation does in fact become more common in the future. So the percentage change in wet extremes here is what's shown in the map, and that does become more extreme over the entire Pacific Northwest, in addition to much of the rest of the land surface. So we're in a situation where extreme precipitation is becoming more common, even in places where you're experiencing some substantial acidification in some cases. So then you can go through the exercise of removing this background trend by subtracting the ensemble mean of the future projections of rainfall in this case, and then recalculating the behavior of those wet extremes. And the relevant thing to note here is that the kind of detrended precipitation shows a substantial increase in the number of wet extremes per century in this case. So I have some global results here. I guess we can focus on the North American one. So the 20th century, I guess what we're showing the boxes go with the 4 different ensembles. So the 20th century projections are significantly different from the 21st century, even though the absolute change in wet extremes is not as large as in places like India or Eastern Africa. But we are seeing a shift towards more frequent wet extremes. So kind of these wet winters that are superimposed on this background trend. And so yeah, I know we're getting up to the top of the hour here, so I'm happy to answer questions about the details of this, but just to reemphasize, the main points are that as a result of these hydroclimate trends that are driven by climate change, we're seeing a situation where soil moisture, so long-term variations in soil moisture, are becoming large enough that conditions we used to consider being a decadal or a mega drought was exceptional are now going to be normal, or potentially even wet in the future. But at the same time, on a year-to-year basis, these extremes in individual winters are going to become more extreme, even relative to a continuously evolving background trend. So in each cases, we're going to need to be considering dealing with both ends of the spectrum simultaneously. So that's all I got there. So yeah, thanks for having me.
Great, thank you so much, Samantha. So we do have a couple questions. Allison, if you're still on, we have a question about how do you recover the devices from the air and the ocean?
Hi there, hopefully you can still hear me. So yeah, the drop-ons we do not recover. They're dropped over the ocean, and they're mainly made of biodegradable materials now, which is great, and they've been made smaller in recent years. The drifting buoys are actually generally recovered. And yes, the radiosondes occasionally, they do say where they've been released from, and occasionally we do get some of those back. But yeah, the drifting buoys, I think, are generally the ones that we do try and recover because they can just have new batteries, I understand, and can go out again. Yeah, thanks.
Great, thank you. One other question for you. Any thoughts on the causes of the number of ARs this past winter, and are they likely to increase in frequency in future years?
That is a great question, thank you. Yes, so this may be better for Nick or Jeffrey, who spoke a bit earlier. I hadn't really been following that season, to be honest, much, but it's really just the steering pattern, so the movement of high and low pressures, bringing in those systems. They're generally associated with an extratropical cyclone, which spins up maybe over the West Pacific and moves eastwards and makes landfall. So they're often associated with those. In future years, again, it really does depend on the large-scale steering. But with regard to actual climate change, we can say that a warmer atmosphere will hold more moisture. So it is likely that in future, then they can hold more moisture and therefore result in more precipitation downstream.
Great, thank you. And then a question for Nick or Jeffrey. What's the drought outlook for central or southeastern Washington for 2023? It seems that there's uncertainty, a waiting game until June or July. Is that true for that part of Washington as well? And what will the cooler, drier conditions mean for fire season in the region?
Yeah, Nick here. I'll go ahead, and then Jeffrey can correct me if it has a different spin. We of course can't predict the seasonal weather, with a high degree of confidence. There is a strong model consensus that the summer is going to be on the warm side, and while we have some warm weather coming in the next week or so, then it looks like it's going to cool off. And so I think we'll kind of have to wait and see, how the late spring turns out. But because of just the way many of the recent summers have been and what the models are showing, I think we can also expect that the summer to be warmer than normal. And therefore, that there's the potential for some drought concerns to emerge. But it does not look like it's necessarily going to be anything severe.
Okay,
and
great.
So, yeah, that's about all, as much as we can say.
Great, thank you. And I did just put the seasonal drought outlook in the chat box as well. And Jeffrey, did you want to add anything to that?
Yeah, I'm by no means a fire conditions expert, but from what I do know is that, the higher snowpack and the expected delayed runoff due to colder temperature conditions recently, and maybe what the longer terms are pointing to is a positive for reducing the potential of fire conditions. The longer that snowpack remains, obviously, is a benefit in preventing wildfires.
Great. Well, thank you to all of our speakers today and for all of our participants for attending the webinar. Our next webinar will be June 26th, and we will see you then. Thank you very much.